Okay, so we are starting chapter 3, which is a chapter on symbolic logic. And every chapter that we cover in this class is kind of disconnected from the chapters that we've covered outside of that. Everything is meant to be kind of its own self-contained topic. So you're supposed to be able to get through chapter 3 without having to really, bring any of your knowledge from chapter 2 into this. However, I will say of all of the topics that we cover, chapter 2 and chapter 3 have the most in common. You will see some connections between those two as we move through this chapter. But chapter 3, like I said, is all about symbolic logic. I like this topic. I think it's extremely relevant today as in this day and age, misinformation is everywhere. A lot of people struggle with making sense out of arguments they hear online and things like that. And this is just kind of a good introduction into the way logicians think about analyzing arguments. We're going to get into the analysis of arguments towards the end of this chapter, but we have some work to do to lead up to that. So to start with 3.1, we're talking about statements and quantifiers. But to lead into that, let's go over some definitions. So symbolic logic, what we're talking about in chapter 3, is the formal study of logic which uses letters to represent statements and other symbols to represent special terms such as and, or, not, etc. In reality, the definition for symbolic logic is much more broad than this, but this is the definition that your book is going to use because it basically suffices to cover everything that we're going to cover. Symbolic logic and logic in general is a huge topic, and there are lots of different types of logic, not just the basic propositional logic that we talk about in this chapter. So there's plenty more to research if you're interested. What we need to define next is a statement. So a statement is a declarative statement that is either true, or sentence is that is either true or false, but never both simultaneously. It's extremely important to understand this idea of what a statement is. It's something that is can always be determined as either true or false, or even if you can't determine whether it's true or false, it is necessarily by definition something that is true or false, and it's impossible for it to be both. Whether a statement is true or false is what we call its truth value. So determining a truth value of a statement is the same thing as determining whether that statement is true or false, but we oftentimes symbolically represent true by a capital letter T, false by a capital letter F. We'll deal more with determining truth values in sections 3.2 and onward. 3.1, we're just getting the basics down. So let's start with some examples of what statements are from a logical perspective. The following are examples of statements. The ground is hot. That's either true or it's false. Now you could sort of debate this one a little bit because the idea of hot could be subjective. So I can see you kind of picking this one apart and saying, well, what's hot to one person is not necessarily hot to another. But kind of ignoring that, we could say that this is a statement. It's either true or it's not. Every human is less than 7 feet tall. This is a statement. This is a quantifiable statement. It's a false statement also because there are people who are taller than 7 feet. Remember, a statement can be true or false. Another example, there exists a number larger than 1 trillion. That's a statement because it is true and carries a truth value. It's not also false, it's just true. 7 minus 5 equals 2. This is a statement. It's even though it doesn't seem like a sentence in the traditional sense, we consider equations like this, mathematical equations, as statements in their own right. So know that a statement doesn't have to be something that's just English or language written in a particular. Oh yeah. So sorry. These are considered statements as well. What are some examples of non-statements, things that are not statements? So this is not a statement. Is there a largest number? That's a question. It's not true or false. It's just an inquiry. We're asking something, not a statement. Throw that couch across the room. It'd be incredible to see, but it's not a statement because that's something that we would think of as a command. You're telling somebody to do something. In itself, that sentence has no truth value. apples are tastier than oranges. So this one kind of conflicts a little bit with this guy up here that I'm calling a statement. This one is definitely subjective, because even more so, I would say, than the idea of what's hot and what's not. Taste is going to vary from person to person. So I may think that apples are tastier than oranges. You might think that oranges are tastier than apples. This is not necessarily always true or always false. It depends on a person's particular taste, right? And then this last one here, this sentence is false. So this one is something that we call a logical contradiction. We'll look at more of these later on in this chapter, but the idea is that it's a statement that cannot be true or false. If it's true, notice if we assign a truth value of t or true to this sentence, then this being true would also imply that it's false, wouldn't it? Because if this sentence is true, then this sentence is false. So now you have something that has both a truth value of true and false, which statements cannot have. If this statement is false, then this sentence cannot be false, because that would contradict what it says. That implies that it's true, and now it's both true and false at the same time. If you're scratching your head thinking, what? You're supposed to, because this is a logical contradiction, making it something that we couldn't call a statement. Okay? So a little bit on statements and non-statements. We are primarily concerned with statements in this chapter. Now, statements oftentimes come in more complicated forms than what we see up here. And what we're going to spend a lot of time looking at are these things called compound statements, which are a way of combining two or more statements. And we'll talk about what those combinations look like in a second here. If you have a combination of two or more statements in the form of what we call a compound statement, then each of those individual statements that make up the compound statements are called component statements. We'll do an example kind of looking at some of those in a second. The specific words that are used to do the combining of those individual component statements in a compound statement are called logical connectives, or we're really just going to use the term connective when we talk about those. Typical connectives are words like and, or, not, if, then. So we'll see one of those in a moment. Let's illustrate this with an example. So for each of these compound statements below, these three down here, we want to do a couple of things. We want to underline the component statements and then circle the connectives. So I'm actually going to start by searching for a connective. The sun is shining and the birds are singing. So the word and is a logical connective because it's connecting these two component statements. I would underline this and underline this. Each of those is a statement in its own right. Notice one of these statements can be true while the other one could be false. They could both be true, they could both be false. Compound statements have their own truth values, and later on, starting section 3.2, we'll start looking at how to determine the truth value of a compound statement by knowing the truth values of its component statements. We will watch a movie or we will go to a football game. So or is the connective combining these two component statements. Okay? If n is divisible by 4, then n is even. N is divisible by 4. That's a statement. N is even. That's a statement. And together, if then, even though it's two words, they form a single logical connective because you need both of them to join these two statements into a compound statement. Okay, so we'll look at those in much more depth throughout this chapter. On to negations next. So the negation of a statement is another statement that is always has a different truth value than the original statement. In other words, it's a related statement that's always true when the other one is false, or it's always false when the other one is true. Oftentimes we think of negations as being the opposite of what a statement is trying to say. So here's a couple of examples. We want to find the negation of these statements down here. The sky is blue. What would the negation of that be? The sky is green? Well, no, because even though that is is different from this statement, it's not a complete negation. We want to say something like this: the sky is not blue. Think about it this way for a second. If I were to write the sky is green, well, if the sky is blue, then this sentence would be true, and the statement the sky is green would be false, right? So one is true while the other one is false. But if something else is true, if the sky is purple, then both statements are false. And in the case of negations, whenever one is true, the other must be false, and vice versa. So that would rule out a statement like the sky is green. However, if we think of it this way, if the sky is blue, then it would be incorrect to say that the sky is not blue. So this being true implies that this is false. Similarly, if the sky is not blue, then it's impossible for the sky to also be blue. That's a contradiction. So if this is true, this has to be false, making these negations of each other, or this being the negation of that. Notice the word not was used. That's very typical in negations. This one, these pretzels are making me thirsty. That's a reference to something, by the way, if you're a Seinfeld fan. So to say these pretzels are making me thirsty, what would the negation of that be? These pretzels are not making me thirsty. Okay. Now, looking at these two examples, it might be tempting to think anytime I want to find the negation of a statement, all I have to do is stick the word not in there. And oftentimes that kind of is all it amounts to, but that's not always going to be the case. So take an example like this. This is another mathematical statement, and this one says that 1 is less than 4. That's true, but what would the negation of this be? Well, inequalities can be a little bit tricky to determine the negations of until you've kind of done a couple of them. There's a table in your book that shows you how to deal with these. I want basically whatever the opposite of the less than symbol would be. And believe it or not, it is not the greater than symbol, because there's a case not being considered here. What if 1 was equal to 4? Neither of these make that a possibility. So the negation of the less than symbol, or the negation of a statement including the less than symbol, would be a greater than or equal to symbol. Now this is true and this is false. This is clearly false. 1 is not greater than or equal to 4, but that's still a statement even if it's false. And we need a statement that's always false when this one is true, or this is always true. If this is false, then this one must be true. Okay, so that's a little bit on negations. So over here is where we start getting into the symbolic part of symbolic logic. Up until this point, we've just been really dealing with some terminology and some examples concerning statements and compound statements. But what we want to be able to do is to start to translate the language that we use of when it comes to statements into some kind of symbolic form. And so typically what we do is we assign statements letter values. For example, the statement, I have $100, might be denoted by the letter P. And a separate statement, Canada is a country, that's a statement, might be denoted by the letter Q. And then we use P and Q in our analysis of arguments involving these statements. Connectives also have specific symbols that we're going to look at here in a second. And compound statements that involve one specific connective might be given specific names that we're going to talk about as well. So here's the 3 big connectives we're looking at here: and, or, and not. In a compound statement involving the word and, in symbolic form, we use this, it looks like kind of an arrow pointing up, and we call statements involving the word and a conjunction. That's the name of that type of compound statement. If a statement involves the word or, we'll use this downward pointing arrow. It looks like a capital letter V, and we call that a disjunction. That's the name of a compound statement involving the word or. The connective not will use this symbol. This is a tilde, and we've already seen that those types of statements we call negation. So we've dealt with a couple of those already. So let's take a look at an example. We have 3 examples here to look at. We're assigning P and Q different statements. P is going to be the statement, the earth is flat. Q is going to be the statement, 9 is a natural number. And what we want to do is translate each of the following examples into language, so that we're given the symbolic form and we want to write words representing these compound statements. So one thing I want to point out here, if you're kind of working on memorizing these symbols. It's easy to get confused which of these arrows means and which ones means or. I like to think of that up arrow as looking almost like a capital letter A, just without that little bar in the middle. And A is the first letter of the word and. So for me, that's the way I remember it. And then or is just the other symbol. So that would mean that this is P and Q. That's how I read that. But let's translate this using what we've assigned to P and Q. P is the statement the earth is flat. The earth is flat. The connective here is the word and. And Q is the statement 9 is a natural number. Okay? Let's take a look at another one. That one was pretty straightforward. This one has a couple of connectives in it. There's a negation as well as a disjunction showing up in here. The negation symbol will always show up right before whatever statement it's negating. So this is negating the statement P, which is the statement that the earth is flat. The negation of the earth is flat would be the earth is not flat. That's the negation of P. This symbol is symbolically representing the word or. Or 9 is a natural number. Okay. So in this one here, we have a combination of two connectives, and there's parentheses being used. So it's important to think about what those parentheses mean. In order of operations in arithmetic, we know that parentheses mean do this first. So basically, this negation symbol, it's not just negating P or Q, it's negating this entire compound statement right here. Now, we'll look at statements like this in great detail and great depth starting in the next section, where we look at truth tables to determine truth values for statements like this. But right now, we just want to come up with a translation for this. So how do we write that? Well, starting in parentheses, P and Q, that's what that says. And we have a statement up here for P and Q. We've already translated this. What we want to do is do a negation for this entire thing, okay? And there's a couple of ways of doing that, but here's how I'm going to choose to do it. It is not the case that the earth is flat and 9 is a natural number. Okay, now here's where you're going to run into a little bit of trouble if you're doing homework in this section and you're doing problems like this, where you're supposed to translate a symbolic statement into English, into words like this. There could be multiple ways of correctly translating this. And so if you're looking in the back of the book and trying to find answers to your work, if you see the book telling you something other than what you have written down, that does not necessarily mean that you did it wrong. It just means that the book went a different route than you did. You can both be correct, okay? Doesn't mean that you're right either. It just means that, you may be doing it a little bit differently. Okay, so last thing we want to look at are quantifiers in this section. Quantifiers have a special place in symbolic logic, and let's give a definition here first. So a quantifier is a word, phrase, or symbol that's used to indicate how many cases of a particular situation exist. There's two quantifiers that we look at. We have universal quantifiers and we have existential quantifiers. Universal quantifiers are quantifiers that look at either all possible cases of a situation or no possible cases of a situation. And you're looking at a universal quantifier if you're seeing the word all, each, every, no, or none is another one. Those are examples of universal quantifiers. Existential quantifiers are quantifiers that indicate that we're looking at one or possibly more of a particular case. And we denote those by words like at least one, or there exists, or some. Those are examples of existential quantifiers. Those are words, but we also call them quantifiers. So here's an example where we want to work with these a little bit. We want to underline the quantifiers in the following statements and identify whether they're universal or existential. So here's the first statement. There exists an even prime number. There exists is the quantifier. It's telling us that it's indicating a certain amount of even prime numbers. This one is existential. I'm not spelling that right. I am. Existential. Okay? Specifically because it's using the word there exists. It's not saying all prime numbers are even. It's just saying that at least one of them is even, or there exists a prime number that also happens to be even. Okay? Here's another case. For every problem, a solution can be found. For every. That's a quantifier. It's saying something about every problem. It's not saying something about some problems. It's saying something about every problem. That makes it a universal quantifier. Finally, there are no planets in our solar system larger than Jupiter. This is making a claim about planets, and it's saying something about no planets. There are no planets larger than Jupiter. Another way of saying the same thing is that every planet is no larger than Jupiter. Every planet in our solar system specifically. So there are no, or you could even just say no. That's the quantifier here, and this one is also universal. Okay? In this section, with quantifiers, we want to look also at negating them. And it can be a little bit tricky to know how to negate a quantifier, whether it's universal or existential, but this little table here will indicate how to do that. So what's interesting about this is if you have a statement that involves a universal quantifier, like all or every or each or something like that, then its negation will not involve a universal quantifier. It will involve an existential quantifier. And we'll take a look at why that is in the example. The reverse of that's also true. If a statement has an existential quantifier, its negation will not also have an existential quantifier. It'll have a universal one. So let's consider the following example here. Some dogs have spots. What is the negation of this? Well, it would be incorrect to say that the negation is that some dogs do not have spots. Because, again, we want the negation to consider all other cases aside from what's stated here. To say that some dogs have spots, negating that would be to say the following. No dogs have spots. Notice that neither of these can be true at the same time. That's necessary for a negation. If some dogs have spots, then it's incorrect to say that no dogs have spots. And if no dogs have spots, it's incorrect to say that some dogs have spots. One being true will imply that the other one is false. Here's another statement. Every day is a Wednesday. So every is a universal quantifier. Our negation should include an existential one. Is it true that no days are Wednesdays? No, that's not true. Some days are Wednesdays, other days are not. So maybe if I use the word some, if I want to negate this, every day is a Wednesday, some days are not. There's what makes it a negation, that not there. Not Wednesdays. Okay? So let's do one last example here. We're going to actually look at truth values for some statements, and these particular statements are more mathematical in nature. Back in chapter 2, we talked about different systems of numbers, natural numbers, whole numbers, integers, rational numbers, irrational numbers, real numbers. And we talked about relationships between those two. So what we want to do is use what we know about those sets of numbers to determine truth values. Each of these statements is either true or false, and we want to figure out which one is which. So there exists an integer that is not rational. We talked about in chapter 2 how the set of all rational numbers contains the set of all integers. Or another way of saying that is that the integers are a subset of the rational numbers, which means every integer is also rational. This would have to be false. Okay? And let's go ahead and move on to the next one. Every real number is a natural number. Is this true? Let me think of this one in terms of a negation. If this is false, then its negation should be true. But what would the negation look like? Well, I used a universal quantifier here, so I do need an existential one to negate this statement. Instead of saying every real number is a natural number, to negate this, I could say there exists a real number that is not a natural number. That would be the negation. Now, is that true? Well, yes, because, for example, the number 1.5. 1.5 is a real number, but it is not a natural number. So that means the negation would be true. I found a real number that is not a natural number. And if the negation is true, then the original statement has to be false. So that's also false. Finally, every whole number is a real number. We know this is true because the real numbers include all of the rational numbers and all of the irrational numbers. And rational numbers include integers, and integers include whole numbers. So every whole number has to be real as well. Okay? And again, this is how we write truth values. Typically in symbolic form, we assign them a T or an F. Okay? Mostly just terminology and kind of getting used to the idea of representing statements symbolically. There's not a whole lot of hands-on stuff in this section, but we'll have a lot more analysis that we're able to do starting in the next. So that's it for this section 3.1.